Okay, last scheduled lecture. We may do some more during summer. But what I'm going to do today is take care of basically three lectures, 27, 28, 29, 30. We're going to pick out little pieces of it. What I'd originally planned to do was this, and this is something we mentioned before, but it's a Clebsch-Gordan, introduction to Clebsch-Gordan coefficients, or Wigner coefficients, which are the matrix elements of tensor generators for any unitary group. And that's something I want to play on today, but I'm not going to derive that probably, but I may be able to get to the point in this lecture 30 to talk about them. But instead, I thought it'd be better to review some of the stuff we've done already, that first. So that'll be lecture 27, which has some stuff in lecture 26 that I have corrected and improved. Then we'll go to lecture 28, which has a good deal of the stuff in 26 and 27 also. But we're going to go directly to do a gyro-rotor rotational energy surface. So to get some idea about this Clebsch-Gordan coefficient as far as spin coupling. It's a physical viewpoint that I haven't seen anywhere else. We're going to see it here. And then I'm going to generalize the rotational energy surface to something called rotational eigenvalue energy, or energy eigenvalue surface. And we'll see some examples of that just very quickly, just to give you a feel for something that's very new and promising. And then we're going to come back and really do what we intended to introduce in this, and that are the magic squares. Introduction to the most powerful mathematical physics notation, I would say by far. Dirac notation is the second most powerful. This is Dirac on steroids. So that's what we really want to get at. So we'll be concentrating in lecture 29 on that, and then showing how it does some really powerful stuff. We'll take on some big molecules, but the biggest symmetry molecule is Mr. Buckyball, which is sitting in the corner over there. And we'll try to talk a little bit about its superfine, hyperfine, super hyperfine, so on. There's incredible spectroscopy that we have not really touched on yet, so today's the day to give it some sort of introduction. So in any case, what I'm going to do is jump now to lecture 27, and we're going to just review page 5, 7, and 8 very quickly. These are improvements of something we've already looked at, but I wanted to make sure you saw it because it's very colorful. So I'm going to back out of this lecture 30 here, look for lecture 27, play that, and then we're going to jump ahead. Actually, I think what I'll do is I'll use the little page thing here to get me right away to the page I want, which is, and let me look over there, page 5. Okay, so I'm going right here directly to page 5. Just to review the asymmetric top a little bit, and we'll look at that briefly. As you recall, we're using colors, mixing of colors in order to show clusters that are mixtures of a irreducible representation symmetry species. That's the thing that I wanted to make sure you saw. And this is a picture that's an improvement on what we had before, just to make the point that when we mix the colors red and sort of a yellow, we get an orange, and these are the orange clusters that make up classical trajectories on a rotational energy surface, whether it's completely oblate, in which there's nothing but orange and cyan, even and odd, coming out of the valley here and up to the limit for that one. Here coming out of the valley and up to the separatrix, so about half of the trajectories are taken care of by this one, the other half by this one, which is a violet color, purple color, blue and red, and a mixture of sort of green and yellow. This is a yellowish green. It's more yellow than green in that particular thing. Now this was very easy to do at Los Alamos in 1980s or so, when they would project the graph onto a 35 millimeter color slide. So you literally were mixing the colors very efficiently. This is not so easy to do nowadays. This is one thing that could easily be done before it has fallen by the wayside. We need to figure out how to improve on that. So there are the yellow and the purple trajectories there. There are the orange and cyan there. The best we could do now was this, and this is a revised color mixing scheme, but it isn't as good as that one. So I wanted to point that out. Okay, and then up further in lecture 27, and I'll just go there very quickly to the end of this discussion. This may be a silly thing to do, but what I want to get to, and there's where it starts. This is page 27. I'm sorry, page 36 of lecture 27 is right here. Now, what I'd like to do is just review this duality, this Mach-Mach duality, the flip side of symmetry analysis, okay? This idea of lab versus body. What we're going to see today, perhaps, is the idea of state versus particle. And particle is sort of a bad word, I think, because we don't really know what particle is. And maybe a chimera. But the idea is that it just boils down to outside versus inside, extrinsic versus intrinsic. So what we've been doing, for example, is writing correlation tables between something that's sort of outside, a global symmetry label, like the octahedral symmetry labels A1, A2, E, T1, T2, correlated with some, say, the mountains that had C4 symmetry, tetragonal symmetry, and we put down their irreducible representation, 0 modulo 4, 1 modulo 4, 2 modulo 4, and 3 modulo 4, and correlate those lectures. That is, the ordinary kind of splitting that you would normally do if you applied a symmetry C4 field from the outside, is you would split these levels that could be split. The singlets, of course, would do nothing but get relabeled 0, 4, and 2, 4 by this table. The E would get split and relabeled into a sum of 0, 4, and 2, 4. And then T1 would split into the Zeeman pattern of 1 and minus 1 modulo 4 and then 0 mod 4. And then the T2 would also split in a quasi-Zeeman form here, but it looks the same except for the middle one, which is 2 modulo 4, because T2 belongs to angular momentum 2. But anyway, taking one of these, for example, we did some work on the tunneling model for this thing. The idea the angular momentum could tunnel from 6 different mountains, 6 different sort of classical local, semi-classical local symmetries corresponding to these irreducible representations, but each one of these mountains has all 4 of those, and we're just looking at one of them in all 6 locations at once in some sort of coherent global resonance between all of the mountains. And the resonance is completely described by the nearest neighbor tunneling, and we've just decided to set to 0 the parameter T, which is crosstown. This is already small, and this is small, small, so we ignore it. And that was something we did right around lecture 19 or so, when we just introduced to the octahedral. And the idea was that when we did that, these 3 levels came out with a level spectrum that looked like this. I've turned it on the side as though it's a real spectrum, but it's just levels. A singlet, a triplet, and a doublet spaced out by 2 to, well, I should say, minus 2 to plus 1. So that was one of our results from just doing this So this is now called a Hubbard model when you do it in solid state physics. But anyway, it's a thing that lets us see the actual waves on the octahedron for each one of those two irreducible representations that are coherent states of all of the different local things, all of the different localities. All 6 of them are in communication and in perfect phase with each other, you see. This is something that's very delicate. If we were trying to arrange it in a machine shop or something, we'd probably be unsuccessful in getting the resonance that's good enough to actually have these. But molecules are perfect in terms of having symmetry, so this is what happens, and that's what we see in our spectra. Now I want to make the point that there's a big difference from doing this outside splitting, you see, this extrinsic or coerced from the outside, symmetry breaking, where you split doublets into 2 things and triplets into 3 things. There's a big difference between that kind of symmetry reduction and the kind of symmetry reduction that you're going to get if these things just get tired of tunneling and get stuck in their local symmetries and undergo what is called spontaneous or intrinsic symmetry breaking. And then we get unsplitting. We get a cluster of levels with very, very fine degeneracies, essentially 0 for many cases, because they're so small that they, in a given experiment, can't be detected. So that's the thing I wanted to make sure that we understood, because we're going to see more of this and the results of this. That's the most important part of this that we're going to talk about today. But this is something I added to lecture 26, and here it is in 27 as well, is that this ordering is independent of where you are in the model that we've been showing so far. There's the A1 T1E, and it's followed by T2 T1, followed by E T2 A2, followed by T2 T1, and then it just keeps on going. You see, even when it crosses the separatrix and makes a new kind of set of clusters, it's the same ordering, you see, it is here. A1 T1E, T2 T1, E T2 A2 would be the next one, you see. And so that's what this wheel is telling, and it's the same ordering basically for odd J or even J. It's kind of going in different directions. But I think that's a really idea. The bands are clusters. Levels maintain order, but change spacing. That is, there's a divorce of these clusters, and they're remarrying over there as the local symmetries are sampled as you cross separatrices in the phase space. That's what rotational energy or a surface really is. And you know this already if you know about band theory. This is the D6 structure that we saw on page 63 and 66 of this, this particular lecture. I think is where that is. I'm now just realizing I maybe gave the wrong one. But when we discussed D6, we saw that there were these clusters, A1, E1, E2, B1, a big gap, and then B2, E2, E1, A2, a cluster might have been a little more spread out, and then the gap might have been a little smaller, and it would come back and do this over again. A1, E1, E2, and that's when counting backwards. You see, it just keeps doing that. That's what this wheel is giving you, either this way or that way for even or odd J. It's the same thing. But as you get above the boundary, then you get the things that were very small, I should say very big gaps. The gap between B1 and B2 now becomes a cluster, you see. And the bands are spread out, you see, that we call a band. Here, A1, E1, E2, B1, you see. It's now spread out, A1, E1, E2, B1, spread out. Lots of space between those levels. So I wanted you to see that that's happening in anything that involves symmetry analysis, and there's a pretty high symmetry with a lot of repetition. You're going to get bands and clusters. That's the way it is. That's the way waves work. So this is very important sort of harbinger to things to come, ways to look at things, think about them this way, you say. Okay, well that takes care of that, I think, pretty well, lecture 27. We're now going to go to lecture 28 and take a look at the gyro rotor. I thought that would be important to see. So I'm going to change over here right now to lecture 28. And we're going to head off to about the middle of it for page 36. And this is something I just wanted you to get a feeling for, another way to look at how spins interact with things before we actually talk about mixing spins up in funny ways. So I'm coming down here to page 36, and we'll play that part right now. It's as you can see, it's quite a few pages, but it's something that I find really important, because whenever you do spin orbit of any kind, and the spin on these molecules is really making a difference in their dynamics, and we're going to see that. But I wanted to see how, in the simplest example of a gyroscope sort of attached to a molecule, what does a gyroscope attached to a spacecraft do? Well, it's supposed to stabilize it. But what if somebody hits this thing with the gyroscope? What's going to happen? Well, it's going to do a dance of some kind. It's anything but stable when the gyroscope is precessing, you see. And that's the kind of thing that we want to analyze. We're going to do it classically first, or semi-classically first. So this is something that I sometimes treat in the classical course without going into the quantum mechanics that much. But the beginning of it's about the same. So the idea is that we're going to have a molecule of some kind, say SF6, okay? And we're going to attach a whirring gyroscope to it, okay? We're going to really constrain. The bearings are going to be nailed to this molecule, to the body frame, okay? So the rotor itself is going to have some angular momentum, and depending on how much you crank up the gyroscope, it's going to have some angular momentum. Could be big angular momentum compared to the rotors, or small, it doesn't matter. There's going to be a total angular momentum of J. J equal R plus X, which in the laboratory should be conserved. So just like on our rotational energy surfaces, these two guys are going to have to precess around that, because that's not going anywhere. But in the body frame, it's going to look like it's going somewhere, just like a J does for our simple case of one angular momentum, so to speak. Okay, so we're going to start off with, say, an asymmetric top. Let's do that instead of SF6. Okay, and then there'll be some coupling. That's what people always like to do when they write Hamilton. There's going to be some coupling between that, and then there's going to be the energy of the actual gyro. The gyro has spin s, so it'll be some rotation constant times s squared. Okay? And in general, this is the difficult part. But not if it's a constraint. Not if you really nail it down. Then it can't do anything. It can't contribute to the energy. Suppose it's zero. That is, constraints do no work. If it's really constrained, it does no work. And this is something about gyroscopes that very few people know. But I call it the zero interaction potential approximation, zip. Okay, we're going to zip it up to our molecule here. And ignore this. Just keep that. And that doesn't do much. Basically, we're going to rewrite this. And this is called what sometimes people call a gauge change. Okay? We're going to write R as J minus S. So we'll get Jx minus Ss, Jy minus Sy, Jz minus Si, each times different constants, 0 for the constraint, and there'll be this constant term. It's not going to do anything. It's not going to change either. It'll be not 0, but it won't add to the complexity. Okay? So that's what you get. You get an asymmetric top in terms of the total angular momentum, which makes so we can write a rotational energy surface, and we also get cross terms that involve now the spin components, Sx, Sy, and Sc. Okay? So that's not good. That's our first order. This is a first order, an odd, time not invariant contribution to a rotational Hamiltonian, which makes it kind of scary. Well, it'd be scary to ride on a spaceship that had this thing that was fully engaged with rotor things off of the principal axes. Okay? So that's really the thing that makes this work, you see. So this changing of Br squared to J minus S squared is analogous to what we do
in relativity, when we want to get the electromagnetic field included in an atomic Hamiltonian, we replace the momentum with the momentum minus EA, sort of a gauge change, okay? J dot S is analogous to P dot A. So that's the coupling, you see. But it's not really a coupling, it's a constraint. And so is that. So anyway, let's look at the rotational energy surface for the simplest, non-trivial, not the monopole, but the dipole. Tensor number 1. Tensor number 0 is too simple to talk about, that's just constant. But it's basically just J, okay? And the shape of this thing is in fact a cardioid, but for small values it's a sphere that's been displaced by whatever the constant is multiplying this thing. So you basically take this thing off center, and then your topography lines correspond to different choices, just like it did in our other cases, of energy, surface, and intersection. And these are the paths, you see, that this thing's going to follow. And it's all going to be, in this case, we use our left hand, okay, for the mountain. And there's just a mountain. That's all there is. It's just a one mountain, not two, just one, okay? And there's the north pole, if you will, of this rotational energy surface. It has a south pole too, but all the trajectories are going the same way. It's not like the quadrupole, which had two, sort of a peanut-shaped thing, and the trajectories went this way on this side, and then they went this way on the other side, you see. This one, they only go this way. It's very Zeeman-like, very processional. It's just like a magnetic field has been put on something, but inside, you see. That's screwy about this. So, if you already had a rotational energy surface like the peanut, and you add the gyro, okay, this off-center sphere to this, that's what you get. Okay, now what's going on here? The S, of course, is fixed to the body, so we can sort of say that the low energy, this is low energy along the S this low region, okay? That's where it's lowest, okay? R is small if J is a constant, and we assume J is a constant, okay? But in the body frame, it's going to move. Its length's going to be a constant, okay? But over here in the high regions, you see, R is large if J is constant. You see, this is high rotor contents. You're down here, you're here with situations where you have small inertia, so the thing is going to be really zipping. But still, it's going to be going that way here, and down here it's going to be going that way, you see, because of this one's behavior, which is left-handed, okay, this way on top, this way on bottom, coming around, that is, okay? So far so good?
Yes.
Okay, so try putting this on an oblate object, same gyro arrangement, okay, add them together, you get that thing. And then this one has two little, shall we say, quiet points, that is stable points. This one really only has one, okay? So this is very interesting. This is a way we can look at this. See here, S fixed, R small, J constant. You got them going in opposite directions, then S fixed, R is large, you see, they keep J constant. Okay, they have to add up to J, you see. Okay, so that's interesting, and we can take this right into oscillator world. All of our ABC oscillators, we're still talking classically, basically. We talk about a harmonic vibration with rotational quadratic spectra. Harmonic, of course, is linear. This is non-uniform. So we're getting those things all mixed up here. And what do you get when you do that? Well, we already know what we get with the ABC model. It just consisted of different combinations of these number operators in single cross terms. Now we have an enharmonic term that looks like that with arbitrary choices for those four indices. Okay, and so you start with this thing and you get this thing as you start to add a little bit more of a angular momentum tensor with number 1 on it. And finally you get what we were seeing, with the rotor. Only now it's vibrations you're looking at. So now you're looking at a way to find local modes geometrically and do the quantum mechanics of them. Angular momentum cones will work here too. Okay, so there's a spherical gyrorotor, a perturbed gyrophore, a really nicely symmetric gyrophore with a local A mode and normal B mode, and B mode's on the other side. Okay, so that's kind of neat. I think that's something to know. So now you're adding the quadrupole and the dipole Hamiltonians to make motion that's really non-trivial. Now, there's analogies between the electronic potential energy surface and all these funny effects that have to do with that, which have famous names attached to them. Frank Condon, okay, that's two famous names, okay, working on what happens when you make a transition between one potential energy surface and another. And if they're different in shape, then you get mismatch, and that causes Frank Condon transitions that normally wouldn't be allowed if they were the same. But now they are. And then if it's off-center or rotated, it's called Dushinsky if it's rotated, but Frank Condon still has his name on the translated, you have it. Ours is the same way. We can have a rotational energy surface down here, make transitions to a higher one, low J, high J, okay? Typically differing by 1 if you want a dipole transition, okay? And the shape or position mismatch opens up all sorts of possibilities, because this is a phase space we're working with. You're still working in coordinate space here. This we can do a lot more with, you see. So you can have two, and now here's an interesting thing. This is called Jahn-Teller-Renner effects, when your two potentials cross and do avoided crossing, or non-avoided crossing, whatever, okay? That's called vibronic interactions. Well, there's rho vibronic, or rho, yes, actually, rho vibronic is what it should be called, vibronic rotor coupling, you see. And how do we make that? And that's just the last thing I want to show you before we go on to this. Here is the one of the surfaces that we had already, okay? But there's two. If we have a spin up, I have one surface for that. A spin down gives me another surface. Okay, so what I have is two surfaces in there, and when you put an energy surface, sphere on it, see where the trajectories are, okay, it looks like Sherman the shark. If you look at the cartoons, you might see I should have a little picture of Sherman, the real Sherman the shark. But anyway, the idea is there are two rotational energy surfaces corresponding to the two states of spin. Very similar to Jahn-Teller, where you put two potential energy surfaces down that correspond to different whatever. Okay? So here's the same kind of Hamiltonian we were talking about before. Only now we're going to make a semi-classical spin. We're going to replace the spins here with matrices. Okay? And when we do that, it goes from just two intersecting Dumbo-like things, okay, two intersecting ones of those, two avoided crossings, you see, that result from diagonalizing a matrix like this. So here's zipped, there's unzipped. That's an actual quantum mechanical gyro rotor. Just to give you a feeling for what's waiting, all sorts of fun stuff that we can do. Okay? All right, I think that's the end of this second vignette of gyro rotors. These are called rotational energy eigenvalue surfaces. At every point on the J vector, I calculate 2 points. Here it's no problem. I just have them already written down. But now I'm letting them feel the interaction, feel the off-diagonal part. So there's this plus this would just be this picture. Then there's something here that makes it have different heights up and down at different orientations of the total angular momentum vector.
So is the off-diagonal term some sort of spin mixing?
It just comes from this. You just write it out.
Yeah.
That's all there is to it.
But the sigma matrices are supposed to represent something to do with spin.
So that's what we used, you see. You put the sigmas in there, sigma x, sigma y, sigma z, and then the classical coordinates of the angular momentum is treated classically. The quantum mechanical is all in the red stuff. Result is you do get a coupling that's dependent on where you are with the angular momentum, beta and gamma.
Well, now I'm just wondering why you wouldn't couple each one of the sigma matrices to each one of the J matrices with some coefficients.
Oh, well, this is semi-classical. J matrices are huge. Yes, you could go and solve this thing exactly by doing that. Well, we want to avoid that. J equal 10, 21 by 21 matrices, then times however the spin is. That would give you an exact solution for, a whole bunch of J's, right? And remember, it's 2J plus 1 squared on top of all of that. So, you want to get a picture of this, not just a bunch of numbers. Just like we doing in the singularity surfaces. Okay, so I think that's it. The only other thing I can show you real quick is that this works really well when you have angular momentum 1 to be the gyro. And this is angular momentum J equals 60. Okay, that's pretty high angular momentum for an SF6 thing, which I simulated quite a long time ago. And there's the Coriolis splitting, okay, due to the gyro. The gyro is vibrations. It has angular momentum. Okay, it makes, when you blow this up, incredible clusters that are due to the eigenvalues this is what these are actually in 3D in the paper that's about this. So it's this matrix right here in the one basis, or you can go in another basis, and instead of PQ and R basis, you can go in the one that we were just looking at, and did it. They're both not diagonal. This one's a little bit more complicated than that one, but sometimes this one's better for various things. So you literally get here, for example, is this particular surface. Then here at these are the parameters, the scalar Coriolis coefficient, which is the thing that depends on how the vibrations have angular momentum or not. Okay, you start to see the thing separate. Finally, it just separates into 3 of the kind of Michelin Man fire plug rotational energy surfaces, or else the cube, which is the inverted one. You see it right there. It just separates into 3 separate ones. Okay, but in the process, it makes some really complicated clusters. There's a C1 cluster, which we've only now seen an example of that. That's an amazing. It's a whole regular representation with a very specific cutting there. So this is the Justin Mitchell's way of drawing it, which is something you can do fairly quickly, and shows whatever you want it to show. You can open up, look at just one surface, and then you can put them back together and see how they avoid cross with each other. Okay, this is a monster. This is what we call a polyad of vibrational things. This one's nu 4, 2, nu 3, which happen to be very close in the tetrafluoromethane molecule. And so there's 9 surfaces, and they're all fighting out to make clusters go in various ways. You could spend your whole life just working on this part of this thing. I think this is a lot more needs to be done with this. Okay, now I'm going to go now to lecture 29, and we're going to start the tableau stuff. As I said, the single most powerful mathematical notation for physicists that has ever been invented. And we'll see some of that power by getting very quick answers to things. Let me go here to lecture 29. And we'll be going down in the middle of that at page 36 to 64. And then we'll go on and look at buckyball. But let's just do SIF4 and SF6 and the simplest molecules, like we've been doing D2 first. So I'm going to just crank this thing right away down to lecture 29, page 36. And you're missing a lot of stuff about Coriolis and Born-Oppenheimer approximation and all that kind of stuff, but we're going to start here.
And they are all already out on our website.
And it's all on the web, yeah. Thank you, TC. Okay, so young tableaus. What the hell are they? And why would you want to meet one? I think this is, although I'm looking at it right now, and I'm wondering if I didn't make a mistake in my choice of, let's see, I'm going to go ahead and play this. I thought that's where it started.
30.
Oh yes, it does. I don't know what the heck that thing was showing me. Okay. The idea of this course was to get you acquainted with the character tables first, but also just the idea of a center of an algebra. In this case, the C2 is the simplest non-trivial group. The only thing simpler is C1. There's absolutely nothing. But this one at least has even and odd. 0 mod 2 and 1 mod 2 is what we call it. The standard is A1 and A2, or A and B, plus and minus. But here's the most elegant notation, right? Now you would say, what's elegant about drawing two boxes? You know, and I don't need to have that there, but I just want to make the connection in S2, S3, and S4. And then a little bit with 5, 6, and so on is what we're going to do. That will be most of the rest of the lecture today. Will be this idea, which is really powerful. But it's based on what Feynman calls the simplest statement of a physical axiom for which we haven't the foggiest idea why it works. One of them is the Bose-Einstein axiom, which applies to integral spin nuclei, and that's what we're doing here. We're finally going to worry about how are the nuclei in this carnival ride, which is going around at a fast rate, and also precessing, and with quantum mechanics it's just going around and doing that on all 6 axes. How are those passengers going to react? They may react about the way I do when I get on one of those carnival rides. I go, bleh! Throw up. At least I used to. I can remember when a kid making horrible messes and not liking the carnival rides at all.
Well, did you clean it up, or did you make the carnival?
Well, you didn't have to clean up because it flew out of the space. Yeah.
Central flame.
Anyway, what are the nuclei doing with a ride like that? Are they doing better than I did? And the answer is, well, sort of. But anyway, if it's a Bose nuclei, which is spin integral, and there are far fewer of those than there are this, and spin a half is obviously the commonest situation, you will take the rotational part, the orbital part, and the orbital means atomic physics will do this too, and we'll mention that if we get to that part, the rotational spatial part, and then there's a spin part. And they're both going to be described by these tableaus. But the idea is that with the Bose nuclei, you put them, the equal ones, together to make a total wave function of spin and orbit, or rotation. With half-integral spin, as I say, which is what fluorine has, so there's 6 of these buggers, 1/2, on all of the tetrafluorides, and there are no other stable isotopes, so you don't have to worry about that, or have fun with that, as the case may be. In this case, you make the spin tableau be the opposite of the orbital tableau. Okay, that means symmetric and antisymmetric, okay, orbits go respectively with antisymmetric and symmetric spin combinations. And we'll show some examples of that fairly shortly here. But the idea is to generalize this, you see, and that's the trouble with the Clebsch-Gordon analysis that we are going to be starting with today, is it's really only convenient when there are pairs. Which is fine for tensor operators, because that's always the way an operator is made, pairs of bras and kets. But when it comes time to look at something more complicated, or multi-particle systems, it's not very pleasant. And mathematical physicists like Rocca and Roger and Wigner, of course, Weil, they have all struggled this, Biedenharn and Lauck. I mean, there's a whole bunch of people that I know pretty well that came after Wigner and Weil that have struggled with this. And we've just added a few little things that make use of these tableaus, which surprise people quite a bit in their simplicity. In any case, for three particles, three nuclei, say our C3V molecule, ammonia, okay? Forgetting about the nitrogen, just the hydrogen. They spin halves, so they're going to play this game. They're going to take the tableaus that are symmetrized and put with anti-symmetry, and vice versa. Anti-symmetry will go with symmetry. For some reason that was missing there. There should be one of those sitting right at that point. But in any case, here's the weird one, right? And the idea is that this permutation group here with a tricyclic permutation, there are two of those. They map onto R1 and R2, 120 degrees plus and minus of the C3V group. And then these bicycles, interchanging just 1 and 2 and leaving 3 alone, or just changing 1 and 3 and leaving 2 alone, or 2 and 3 and leaving 1 alone. There's sigma 1, sigma 2, and sigma 3. Okay? So the idea is that this character table maps onto this character table. Okay. So far, all I've done is draw funny pictures that look very clumsy for these nice little A1s, A2s, and E's. Okay? But let's just go one step further and see how they work. Because remember the vigor with which I sold you the idea of a subgroup chain. And the subgroup chain could have been for C3V either. C3V is bigger than C2, which would just consist of that element and the identity. Or it could have been, we could have chosen a C3, which would consist of this and the identity. Okay? Those are the two main types of choices that you could make. There was only one type of the three, that was the normal subgroup, but there were three types of the sigmas, because they weren't normal subgroups. Okay? Well, I said that that's the way you divide and conquer the group. This is already built that way. You can see very clearly where the classes are. The classes are indicated by what we call partitions. The number of partitions of 3. Okay? These are the 3 partitions of 3. And there's three types. These two are the weird ones. This is parasymmetric. This is anti-symmetric, and that's symmetric. So here's always in mathematics, when you put 3 things down, and you can solve that, and you're pretty well home. And this is what Young did, really. Alfred Young, a minister in UK, a long time ago, invented these things. And only just scratched the surface in their application. Here's 4. Okay, now we're talking about tetrahedron. Okay? The tetrahedral group, this guy, with his 4 spin a half, say, and we're going to have some examples of the spectra for that very shortly here. This has 4 to the factorial permutations, consisting of the unit operator, in which nothing moves, 1, 2, 3, all in parentheses. A tricycle, and there are 8 of those. They are the R1 to 4, and then the R to 1, 4 squared. That was a class of order 8. And then remember our 180 degrees on the Cartesian axis, okay, of this thing. The tetrahedron still has that, okay. I can turn around any pair here, you see, and that counts for 3 type of things like that, okay. And I'm not writing them all out, obviously. There's a 1, 3, 2, 4, right, and then a 1, 4, 2, 3. So, you know, keep that in mind. And then there's 6 of these. Remember, there were 6 rotations by 90 plus or minus, corresponding to 3 axes, x, y, and z, and then going on the other side of the axis. Well, they have to have an inversion if you're going to be talking about tetrahedron. So it's I times 90 degrees And this one too, I times 180, which is a reflection, a mirror plane reflection for the tetrahedron is right through there, right through there. There's 6 of them that you can find, just like you can find 6 180-degree I rotations, I1, I2, I3 through I6. So this is isomorphic to our octahedral friendly group. So you should be, you know, getting to the point where you can, on speaking terms with this fellow. Okay? This is the elegant way to handle that. This is really amazing. Because you see, it's automatically giving me the first column of the characters. So it did this. All I have to do is add 3 to this in a lexicographic way. I can put the 3 here and make that. I can put the 3 here and make that. Then I can take the 3 and put it here and make this, and then I can put the 3 there and make that. And you're done. That's all there is. Now I take each of these and add a 4 to it, either on the end, that's the totally symmetric A1, okay? And then I can put a 4 there. That's going to give me this guy right here, okay? I'm done with this guy now. Now I'm going to go to this one. And the first thing I do is try a 4 here, okay? And if I can find that guy, it's the last one here. Okay, you can see the dark ones are the ones I'm putting on the last time, right? So I get that one, okay? Then I can put the 4 there and make that guy. That's A2. And these are parts of, respectively, T2 and T1.
Is there any relation between this enumerative construction and induction of a group from the subgroup?
Well, what this does is just lays open the Frobenius reciprocity, which is the theorem that says if you do a subduction, you use the same table to do the induction. That, I mean, that's really the best way to say Frobenius reciprocity. Otherwise, you spend 2 pages of proof in all of the math books that I've seen, including the ones for physicists. And those are the ones that physicists won't read because the proofs are, you know, just opaque.
They don't know what a functor is.
But, yeah, there's too many things they don't know. Although they really do know it, they just don't feel like they know it, and that's what makes them turn on the way. Anyway, you end up here, after you put a 4 on this one, you see, and you can put a 4 on this one a lot of different ways. You can put it here, you can put it here, or you can put it here. When you put it in the crotch, for this one and this one, you get these 2 guys. That's E, with a dimension of 2. Okay? But we still don't have all of the 3s until we finish putting the 4s on everything that we can. And there they are. There's a triplet right there. That's the 2 triplet. And I've turned the table around. I usually put T1 here and T2 here. I flip them around so that they are the way we would normally do it with S4. Okay? So already it's given us some power. Already we have some power. But now let me show you how it gets magic. I'm going to push this guy aside and just remember what we're doing here. When it comes to Fermi nuclei, which is mostly what we'll talk about today until the very end, symmetric, antisymmetric. Mostly symmetric, mostly antisymmetric. Parasymmetric, para, and anti, they're the same. You just use those 2 right on top of each other. Now, if your orbit or rotation is mostly antisymmetric, you use a mostly symmetric tableau. And that's all you can do to make an antisymmetric Fermi, let's see, what was the other guy with Fermi? Pauli Fermi, Fermi, well, there's 3 names associated with this. This is Bose-Einstein, and this is Fermi-Dirac. Dirac has got his name on that because he wrote some papers on anti-symmetry, obviously because he was doing gamma matrices. So, that's what we're after, but here's what we have to do. We have to make a subduction, a correlation, induction, subduction, correlation table. Really, for our molecules, you want the parity in there too, and you certainly want that for TD. So this is O3 to TD correlation. that's going to work here. And by the way, this is all reviews of modern physics way, 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 way back in the Stone Ages, okay, that I wrote. One of the first reviews I wrote. And I've been using this thing ever since. And it's slowly now getting citations. It takes a long time. It's just, you can see the curve on the exponential sort of going up a little bit here. Okay? So, that you know, it's hardening. They're not as inertial as I thought they were. Anyway, we'll do the methane-like molecule for a while here, as well as SF6, which is requires a little bit more than that. That's what SF6 requires. Now, the thing that I left out was the formula. I might jump to that real quick here. In that Reviews of Modern Physics paper, there it is. It's Appendix C, character formula. It's called the Coleman formula because somebody actually worked this out in 1966. Okay, and there it is, but it involves some tech. But anyway, it's a couple of steps, and you get a character for a monstrous group, S69, partition 21156. Okay, it just, you know, it's very, very elegant, and I'm going to show you something even more elegant, which is the dimensions, which is what we really need here to calculate our spectra, heights, how tall are our spectra. So here are two formulas. Now, don't look at this one first. I should have split this off, and maybe I did. No, I didn't. I should have split this, and you didn't look at this, and you just look at this. But here is the Young-Tableau-Europe dimension formula. And this will work with a tableau that's as big as you want. You can do it by hand. Let's take the ones we already know as examples. You take n factorial, write it out, and then you take the tableau and you stick in numbers at each box that represents the length of its hook. And a hook is just doing, doing. Okay? And did I do that right? Yes, I did. 1, 2, 3, 4, 5, 6 goes there. 1, 2, 3, 4 goes there. Okay? 1 goes there. Nobody this way, nobody this way. Okay? You always look to the right, you always look down. This one right here, 1, 2, 3. Same as this one. 1, 2, 3 goes there. But everything on the edge is going to be 1. You got the picture? Let's try this one. 1, 2, 3, 4, 5, 6, 7, 8. 8 goes there. That's all you need to know. Hard, huh?
Well, how do you prove it?
An elegant physical proof of this, the closest I can find is Herbert Wilf at the University of Pennsylvania. I wish it's one of these things where I should have gone to see the guy. But he had this elaborate thing where he had a wartime analogy, must have been in World War II or something, where parachutists would come down, onto the field, and they would walk and wind up according to some rules at various places. And from that he could get a hook length formula. Now I didn't follow the whole thing, but it looked interesting and it looked like a possibility. Since one of the things that he was interested in was physics, and he was very fascinated with our formula, order of group equals sum of squares of these dimensions. Right? I mean, for S3 we've got 1, 1, and 2. The sum of those squared is 6, which is the order n factorial, 3 factorial. Okay? But anyway, you see how it works. For this partition here, I put it downstairs and go hook length, 1, 2, 3. And it cancels the factorial, so 1. This one does the same thing, 1, 2, 3. Cancels the factorial again, gives me 1. So that's the 2 1s in the character table that started off. But this one is a little different, you see. It's 1, 1, 3. 3 cancels the 3, leaving me with 2, which is the answer. Well, have fun playing with this, because it hasn't failed me yet. We've taken some pretty big molecules into account using this. This is what TC thesis really was, to start with anyway, was working out the spin weights of that buggy right there. Okay? Now, here's where the tone shifts. If you have a symmetric group, you have three things that you can permute. Okay? Now, that would be very classical. That is, that you have particles that don't get lost or have uncertainty relations, okay, that you move from place to place, always keeping them in the box that you originally had, egg crate that you originally had the eggs in, okay? What this is you not only do that, but you allow each of them to have m quantum states. Okay? In other words, you allow linear combinations of all the eggs in a space that is m-dimensional. That's a big jump. But what you're finding are the irreducible representations of the group UM. And it's those tensor operators that define all Hamiltonians that we know of. Certainly all Hamiltonians in Hilbert space, because that's the group that we're working with, but it's also going to work for relativity, the finite representations of a Lorentz group. Okay? So all you've done is, if you have n particles and m dimensions, basically it's that duality thing again. You have particles and you can label those. That's one group. Then you can go ahead and you can do permutations on the n states that would label states. You see, particles get labeled, states get labeled. That's like lab and body. That's the duality of the permutation group, roughly speaking. Okay? But you can let linear combinations go on this one, and you're doing stuff that people know about. That's called making the tensor representations of UM. You also turn it around and make it sm.un. That thing can give all the operators. It can make transitions of the things that you just built the other way. So this has hardly even started the power that's residing in this notation. But anyway, here's what you've got to do. Instead of doing n factorial, the denominator's the same here. Okay, they both are using the same numbers down here. But instead of doing m factorial, or n factorial in this case, okay, you do this weird thing. You take the tableau and put the m on the diagonal, and then m plus 1 first off, m plus 2 second off, so on. And then you do minus 1, minus 2, minus 3. For example, instead of getting a 2 here that we get with factorial, we take this product, okay, and it's U3 we're interested in. So I put a 3 in there, okay, and then it has a 4 there, and I go down by 1, that's a 2 there. There are my hook lengths that I used up here. The 3's cancel, and I'm left with 8. Now if you know any high energy physics, this is a Nobel Prize right here. This is the eightfold way. This is the, we might call a vector representation, the regular representation, the regular representation of U3, the quark group. Then the Nobel Prize actually given for this one, the discovery of a particle that became part of a decaplet. So now I put the symmetric representation 3, 4, 5 over 3, 2, 1. That's the decaplet. The omega minus particle is the only particle missing from that, and it was discovered in this Gell-Mann's Nobel Prize. Okay? Now they had really complicated formulas to get everything about the U3 group. We don't need them anymore. And we use them for things where we know it's U3 symmetry. They still haven't figured out what U3 symmetry is. They just made it bigger. Okay? Now here's what we use it for. Now before I go there, let's take a simpler case of this one. What would be the dimension if it was spin a half? If it was spin a half, That's 2 states. That's U2, right? So I put 2 here and 3 here, right? And 1 here. So it's 2 and 3 over 3. It's 2. Right? That's just giving you a doublet. So this is a 3 spin-a-halves. If one of them is paired up, you only got the other one working. So it's just like spin up and down again. You've got up here and down here. They cancel each other as far as pairing goes. No symmetry. They're totally anti-symmetric like you're supposed to be, and you're left with just one. Okay? What would we get here? We'd get 2, 3, 4 over 6. Okay? That's 4. Spin 3 halves. It's a spin 3 halves. 3 halves all symmetrized gives you an angular momentum of 3 halves, which has 4 states. Okay? Now we're going to use that one those simple ones right away here. What I'm looking at is a tetrafluorosilane spectrum, which has fluorine, so we're going to be using the same numbers as methane. Hydrogen and fluorine both spin a halves. It's just that hydrogen has isotopes. Deuterium to start with. Okay, and then tritium is the next one. I won't go to that one. But, and I forget what the spin of tritium is right offhand, but I'm guessing it's 3 halves. But anyway, spin 1 for deuterium. Okay? So it's a U3 creature. This is a U2 creature. Okay? So, and what I've got is 4 particles now. So what I'm going to do is take this tableau right here, okay, and put this one with it, because it's a fermion. I've got to do that. And deuterium is a boson, so I got to put this one with itself. Well, as far as A1 goes, A1 plus anyway, there's nothing. You see, I'm going to get a 0 in there. Dead. Okay, that one can't be used. Okay, but this one can. This one requires totally symmetric, so I put down 2, 3, 4, and 5 over the hook lengths 4, 3, 2, and 1. Result, 5. Angular momentum, 2. This is a tensor spin that goes with the totally antisymmetric rotational wave function. Then we go on to the next one. Okay, for methane, I only get 1. I put in a 2, 2, and then a 3 off diagonal and a 1 lower part. Multiply that by hook lengths. 2, 3, and 2. There's a 2 there because of that guy sitting there in the one corner. It's this tableau, right? That goes with itself, right? Because it's self-conjugate. Okay, so that's the spin one we're going to use if that's the orbit. All right? You get the picture here? Now this one has to go with that kind of tableau. But when it comes to deuterium, it wants to go with its own kind. Very different behavior most of the time here between deuterium and thing. But this is the one case where they give the same dimension. It's kind of weird. But this one is really extreme. This one gets 15 for the CD4. It doesn't exist for CH4 or CF4. Okay. But what does exist are the parity doublets. So this is an actual picture here of those plus and minuses as they are allowed by the correlation table that I pointed at before, and I'm not going to go into details of that right now. This is the most complicated calculation of that involves parity and permutations, but once you get used to it, it's fairly simple. Anyway, what does it predict? Let's go ahead here just a little bit and see what the transition looks like in one of my two-dimensional nomograms, what I call a spectral nomogram, where I put the ground state here and then an excited state, which is crossed with a vector vibration, dipole excitation of vibration. Okay, so I'm going to have all of these things. I'm going to have a 6. That will be the P7, and that's what we're looking at right now. But then up here is going to be a Q7. That's for status quo. This is for plummet. And then there'll be rays. There'll be an R7 even further up the line there. All of them will have spectra that's more or less like what we're seeing right here. But what I'm interested in the heights Okay? And you see this one has weight 3, this one weight 2, and why does it have weight 2? Because it's got plus and minus for the E. This guy right here has only got either plus or minus, so you have to take these numbers straight away. Then let's see what else we got here. F1 and F2, they come in definite plus or minus things, so their weight is just 5. If I see that right here for the A2 right here, and then these guys have weight 3. Okay, I'm sorry, putting it down. It's 100 the same for deuterium and hydrogen. Okay, so that's where when you have a transition that's involving these are the intrinsic things. The other stuff, the angular momentum, is extrinsic. Okay, this is sort of the soul of the nuclei. The spin structure inside has 3 components, 2 components, and 5 components respectively. We'll see better diagrams of that for the cluster stuff anyway. But you can see that all of these things have a height of 3, and the E only has a height of 2. Okay, and then the A here sticks up with a 5. Okay, so that's just to give you a feeling for how we actually do the accounting of this. But anyway, we've been listing the clusters for this thing. Remember, A1, E, F, T1, T2, T and F are interchangeable as notations for these groups, tetrahedral and octahedral. Here's 5, 3, 3, and 5, which makes a total weight of 16. It's called spin weights. This is 3, 2, and 3, that's 8. Okay, and then you can actually see individuals here in the separatrix region, more or less obeying their weights. And this one a little bit low than it should be, but that's because it still hasn't really formed. It's kind of like this one. And then that has a weight of 6, that has a weight. These are cluster weights now, where you're adding up all of the weights in this case, 5, 3, and 2. Now, what does that make? 10. I should have a 10 there now. That's a typo there. Okay? So there should be 10 here, 6 here, 6 here. Okay. So we looked very close at the energies of this thing based as a rotational energy surface. Now we're looking at the spin weights that make their altitude, so to speak. Okay. And here's a complete picture of what really happens. And this is where you take the tableaus and let them mix to make broken tableaus. And this is something I'm going to try to explain a little bit. But anyway, there's weight 2, weight 3, and weight 5. You can see what makes the 5. There's 5 of these things. That's it. There's 3 of these things. That's it. But there are 2 of these corresponding basically to parity. These are only allowed to have a certain parity, not plus and minus. That one is the only one that manages to get plus or minus. And the same thing would be true here of tetrafluoro. I'll skip that for now. What I want to show is this extended. Remember spontaneous symmetry breaking, coerced symmetry breaking? This is entanglement. Okay. Now we're talking about SF6, and it gets entangled. So we use a correlation table of a global symmetry, octahedral, against a local symmetry of its mountains. And if we're interested in quantum waves that have settled in the mountains, the C4 mountains, then that's the correlation we want. But regardless of where it settles, as far as octahedron and internal groups, the really central, shall we say, the brain and heart of this molecule are its spins. So what we have to do is take account of the permutational symmetry of this 6 nuclei. Perfect symmetry, absolutely really hard to break. Really hard to put a mark on one of these things that breaks its symmetry. Idea is that S6 symmetry is big and perfect for this molecule. So here's the ultimate global symmetry or you could look at it as the ultimate intrinsic symmetry, and then correlate it with the octahedral symmetry, which is now a small subgroup of this. S6 has 720 elements. There's a lot of cosets of 24 or 48 in this group. Okay, so that's what we're looking at is a table that comes from working the characters of this S6. And here is the singlet, weight I equals 0. Okay, and you'll see that what we will be making here, EU, you see, will have this guy right here. And you can see there's two boxes that aren't paired, so that's got to be a spin 1 with a triplet. This has got 4 boxes that are free. Okay, that can make us angular momentum 2. And finally, this one can make an angular momentum 3. That's 6 1/2s. This is 4 1/2s that are free, and this is 2 1/2s, which gives a 1. Okay, so those are the spin weights that are associated with the tableau, but these symmetry species only pick a few of those in each case. Sometimes they only pick 1, just like methane sort of does, except for parity. Here, T2G picks off both a singlet and this guy right here, which is a quintet, 5. 1, 2, 3, 4, 5 things are going to actually show up in a hyperfine spectrum. Okay, and then A1G picks up on that. A1U picks up on the same thing. Okay, and then A2U, it got 2 combined. All right, so that's what we're going to see. We're going to see, these are very greatly simplified sketches. I'll show you a better picture in just a minute of the high resolution, super high resolution of SF6 spectroscopy done by the Bourdet brothers. There's a Jacques Bourdet, it was not on this particular paper, but and Christian Solomon, Oliver Pfister. Oliver Pfister's at Virginia right now. Christian Solomon's still in France. This is an amazing piece of experimental work to get these, and I'm really glad they did it because I wouldn't have had anybody believe this stuff otherwise. This is the basic idea of what's going on here. Is spontaneous symmetry breaking is occurring because you get stuck on the mountains, and as soon as your angular momentum gets stuck on the mountains, well, then you have not identical nuclei anymore. These guys down here are sort of bums in the tropics, Margaritaville. They like it hot. Okay, they're going around zip, 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 zip. Or these guys are stuck out in the cold in the North Pole and the South Pole. That's going to split them out. That's going to split them out, either this way or that way. Depends. Depends on whether this is higher energy or that's higher energy. In one case, you're going to get a singlet of triplets. In the other, you're going to get a triplet of singlets. So that's basically what this boils down to. So this is really a thing that's very complicated mathematically in some ways, but physically quite simple. It's the molecule doing NMR on itself. And that is neat. So here's some typical spectrum. Now this is the whole PD88 thing. And we're just going to look at one transition right here, which actually turns into be quite a number of transitions. Actually, there's a possibility for 9 transitions with the experiment that they do. And this is where relativity and quantum meet. And you need to do them both in order to really analyze what that cluster is going to look like. And I'll show a picture of it right here. What's really interesting is that in this thing, forbidden species, e.g., not allowed, E has to be odd. T2U, T2 has to be even, T2G only, you see. And A2G, it's a forbidden. It doesn't show up here. Only A2U. So A2 has to be odd. That makes a heck of a difference in this fancy spectra that they do. You get a relativistic crossover resonance because of the mixing of EU and T1U. T1G doesn't participate. T2G and T1G have slight participation, but it gets lost in this one. T2G and EU do not, so you don't see something there. this is where we really scored a big deal, because all of the people that have been doing sort of the sloppy group theory had come up with equal parities on every one of these symmetry species. We showed that there was no EG. And this is a case where the thing is solved by the dog that didn't bark. There was no barking here. If you remember the Sherlock Holmes novel about the why did the dogs not bark? Because the owner was the one that came in and did the crime. All of quantum mechanics is zeros, right? It's the magic of zeros, of things not happening. Okay, so that super hyperfine spectra, this is what we had to do to really analyze what they would be seeing. And they did see it finally. There it is. I actually saw pieces that looked like that. It turned out to be a quintet of triplets that told you that the North Pole had more energy than the equator. And this is a really amazing look inside a molecule. Anyway, here's weight equal 8 equal 5 plus 3 for E. 5 plus 1 is 6 for that. This is the single finger salute, right? I won't do it for the camera. But this is the Martian 3 finger salute right here that comes with A2. That's the 7 plus 3. This is 5 plus 1. So this is an amazing piece of machinery, this SF6. It's over here hiding. It's very bashful. Amazing symmetry going on. And this is just one of the clusters, the cluster E, T2, A2. The others are interesting too. That's the thing. Now, if the nuclei had all been spin 0, there'd be nothing to do. Hundreds of lines would vanish. I'd only have A1G. And there are only a few of those. All the rest of them are gone. Now, I don't have a molecule that's got a spinless hexa whatever. I don't have a nucleus N that's a hexa N. But I do have these guys. Spherical top molecules that spin 0. Okay? That's our buckyball. All right? It's the icosahedral guy right here. You don't have to move, I'll move it. Okay, this guy right here, and you can make nice shadows with it that have various showings of symmetry. But the basic idea here is with C12, that's a Bose ball. I don't see any of these, but we do have osmium tetroxide. So there's an example where all the spin species go except a very few. Now, there is a carbon-13 isotope that has spin 1/2. And of course there's SF6 in hundreds of hexa things, as well as tetra things. Okay, so spin 1/2 is no problem, we can find that. But so far, we haven't done the experiment where we put every one of them carbon-13. TC's thesis was to just put one of these carbon-13 and fool with that. Okay, that's very interesting when you do that. You get a very weird rotational energy surface because just one neutron on this monster completely destroys it. It's like Achilles, the great hero from the ancients, right? This perfect human being, except for that lousy ankle, right? The hilly heel, right? His undoing. All it took. You have a perfectly beautiful symmetry and you put one thing here, you reduce it to C1 from this enormous icosahedral symmetry, which is basically an S5 normal subgroup. You reduce it to nothing. Because you see all of these things here are sitting on a site that has no local symmetry except reflection. So you basically reduce it to CV if you count the reflections. What a fall from height, you see, you have. Completely screws the thing up. All you have to do, if you put 113 in there, these things were all forbidden by Pauli, Fermi, Dirac, except for those two levels at j equal 50. Here's what j equal 50 looks like. You put one neutron on there. 202 levels suddenly show up. And it's totally lost its symmetry. Has no rotational symmetry at all, only reflection. Talk about fall of the mighty, okay? Now I ask the question, where did those 200 levels go? I had 2 before, now I got 202. Okay, where did they go? Better question, where did the 1.15 octillion levels go that this thing has? This has got 2 to the 60 hyperfine states. Now you say it's only an order of magnitude to go from SF6 to this thing. That's right, it's an order of magnitude in the exponent. Right? You've got 2 states for every one of those guys, so there's 64 hyperfine states in this thing. There's 2 to the 60 here, which is 1.8 octillion. And it's beautiful. We've looked at it a little bit. This is the buckyball vibrational stuff that Dave Weeks did, and also I was the one that first did the rotational thing. This is what we predict for C12, which has its 2 lousy levels at j equal 50. We're looking at P at the 50 on this P branch, okay? And here's what you get with 13. And I mean 13 60-13s, okay? Most of the hyperfine states don't like it, but you get this wonderful distribution. These are all statistical weights. You can plot it here. It's pretty amazing, I think, to contemplate what that molecule will do. The thing can be a computer, maybe, if you could control all that stuff with microwave. These are just some pictures of buckyballs doing things, showing its basic golden ratio TH symmetry, one of them, one of the 5, okay, and putting 60 carbon atoms, 1C at each vertex of the soccer ball, or 1C on each of the pentagons, and there are 12 of those. 12 times 5 is 60. There's a rotational energy surface. There's a typical set of clusters that we would see. We were hoping that we could see the molecule. For years we couldn't prove the molecule existed, so I was thinking of all the ways to see it. So vibration turned out to be the way, at least at first, but nobody believed it because people don't really believe the symmetry analysis of vibrations. Like the people that count are the chemists.
It looks pretty solid to me.
Pardon?
It looks pretty solid to me.
Yeah. Well, the idea is that these are the T1Us. Those are the only ones that should be dipole active. So we expected to see 4. And it wasn't until we had pretty much given up, it was going on to other things, that August, I remember it was in August, I got a fax from Don Huffman, and he was working with Wolfgang Kratschmer and Klaus Berlus at Max Planck. He's at the University of Arizona at his employment. And our spring model and the spectra fit pretty well.
Here we go.
And there they were. Before we just seen nothing. But he did an amazing thing of putting a dusting on a perfectly smooth silicon bar, and then do a grazing spectra. So he got the cross section up, and he could see those 4, and some other stuff too that later turned out to be important. And as he said, we had much fun with your program. And the program was a little Mac fireplug that did all of the movies of all of the modes, not just the dipole active ones. As he says, things are moving fast in the bucket. He had no idea. It exploded after that. And 2 or 3 forms of carbon are on my license plate. You see the diamond and C60. And graphite, that's what you use to make the black. So there are 3 forms of carbon on that. No graphene yet. We didn't know about that when I did the slide. Okay, that takes us up to lecture 30. We started a little bit late, so we have a little bit of time, I think, to go ahead and do just a bit of the tensor stuff that is so important. So I'm going to escape from here and go over and get number 30 out of the box and go ahead and play that. And this one's very rough, but it's a good idea. The idea is I want to try to show you that the Clebsch-Gordon coefficients, what they do, I want to show what they do, and that, as I say, is a whole good part of a course on group theory right there, and really you can make your whole career trying to find better ways to handle the Clebsch, and I think there are better ways, but we've only got an inkling of how to go on that so far. But I'm going to take the simplest case, hydrogen, atom, atomic hyperfine structure. Can't get any simpler than two spins, one for the electron and one for the proton. And here are those outer products. Spin up, 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 down, up, and down, down. Can't get much simpler than that. So we've been doing these outer products that we talked about, only just with two things. So this is very finite. I don't have truncating. Okay? And the idea is to take the spin-and-a-half representation that applies to each of these objects. The proton and the electron both have spin-and-a-half, both use this transformation matrix of Euler, the Euler thing that we have shown many times here in this class. So when you do an outer product of these two, get a four-dimensional representation of this thing, you're working with an outer product symmetry group, proton cross electron, U2 cross U2. Now this is only a symmetry if there's no interaction between those two. And we know there is. There's a big interaction. The Fermi contact interaction is enough to make the 21 centimeter line that we use in astronomy to tell how much atomic hydrogen there is. So, the interaction reduces the symmetry to only elements where the electron rotation is the same as the proton. So if the proton and electron are like this, that's still a symmetry. That's not. That's not. That's not. Only that. Okay? So I'm going to reduce this by making those angles all equal.
Professor Harter?
Yes.
Right here, you start with the D1/2 rep that contains alpha and gammas, and you haven't yet accounted for those there in the middle. Do they go away, or are they yet to be
I am just doing
okay.
the Y. They're pretty easy to tack on at the end.
Okay.
And to get the Clebsch-Gordon coefficients, I don't need them. The Clebsch-Gordon coefficients for them are fairly simple because they're cyclic and commutative. They're part of the diagonal. So in a sense they do go away, but I am just making them go away here. And then I'm discovering that this matrix, symmetric and anti-symmetric, that's all you need to know is that those two guys have to be symmetric and anti-symmetric, okay? Or just spin up, up, and spin down, down, okay? And I think I've got that one here. That one looks like they got schmooshed there a little bit. Let's see if that's right. No, if you do a transpose, there it is. It's okay.
Yeah, they're true.
Yeah. Anyway, that's a table of Clebsch-Gordon coefficients. That's what that is. It will reduce this matrix to this. In other words, it'll give you a block of angular momentum 1 and a block of angular momentum 0. That's the symmetry way of looking at it. So irreducible, this is irreducible of this, but it's not irreducible of this. It becomes reducible. And so that's the way to look at it. There's the vector part of the transformation, the blue, which is giving that block right there. And then there's the scalar part, the anti-symmetric part, giving me spin 0. So I'm looking at a Young tableau that's anti-symmetric for this one. You see the 1 and minus 1. And then it's symmetric to permutations for the other 3. This is just up, up. It's obviously symmetric. This is up, down, plus up, down, up. And then this is down, down. So that's all there is to the Cleffer-Gordon coefficient table. This is the way the tables are often given. And that's the notation for them. A half cross a half, and then the two m numbers, proton and electron, summing up to give a total m, and then the 1/2 and 1/2 either summing or differencing to give a 1 or a 0 that you see on top here. 0 there, and then 3 ways to make 1. So this is the formula for a Cleffer-Gordon reduction of an outer product. Cleffer-Gordon coefficient matrix on this side is this thing. The Cleffer-Gordon coefficient matrix on the is transposed, but that's understood in the sum here. And that gives you either a D1 or a D0 representation outside. And the coupling gives you either a triplet or a singlet. The question is, what are the energy levels? Well, that's something you can spend your whole life on as well. What's observed here is a 1.4, let's see, times 10 to the third here. Let's see if that should be a gigahertz. This is 1.47 gigahertz. This is 10 to the 3. Let's see, no, I guess I've written the whole thing out, plus or minus 0.3 hertz. That's the 21 centimeter line. Now here's a quick way to get the eigenvalues. You just take the interaction Hamiltonian, which is this, and write it in a binomial expansion minus the square terms. So this is J total, this is J proton, this is J electron squared. So you want J times J plus 1. For the J squared, you want a half plus times a half plus 1. Okay, that's 3/2 times half, 3/4. Remember, that's what we get for spin a half, is 3/4. And you got another 3/4 here. So this is the formula for the eigenvalues. Very quickly, this is Rocca's trick, as they sometimes call it, for getting eigenvalues in situations like this. And he did for more groups than just 0.3. So that's the stuff here that I'm going to just sort of zoom through. If you go and read about this in chapter, let's see, this would be, I thought I had put this on this thing, but obviously I didn't. This is the beginning of one of the units.
I see it listed at the top here, chapters 23 through 36 of QTCS.
Yes, Unit 7, chapter 23 and 26. And it'd be 23, because it's the very beginning of the discussion of the Cleffer-Gordons. Anyway, you do the matrix with both a B field, and the coupling. Okay, the B field is diagonal in the basis of the outer products, but not diagonal in the basis of the symmetrized and anti-symmetrized products. As you can see here, we've got some off-diagonal terms in terms of them. But then, while this is diagonal here in the product, it's off-diagonal for the interaction. The interaction is off-diagonal. But the interaction becomes diagonal in the total angular momentum basis that uses the Rocca trick. Okay? But we want to combine this right here with this and diagonalize that, or else combine this with this, diagonalize that. You should get the same answer. So that's one of the things you can do. You can play it against each other, make sure you're getting the right answer. And that means a whole set of curves, avoided crossing for the thing that becomes a singlet here and a triplet here. You see there's a singlet, there's a triplet. And the triplet splits in 3 ways. 2 of them are very trivial, but one of them is like an avoided hyperbolic crossing. And as you make the p moment bigger, p moments are pretty small compared to electron moments. And I think you'll see that if you look at those numbers that we have. Anyway, you can see the symmetry is playing a role here. If I do j equal 1 cross j equal 1, I get 2, 1, and 0. The 2's are symmetric, you see, to permutation. The others are anti-symmetric to permutation, the 1's. And then there's a scalar, which in this case is symmetric. It just does the 1 minus 1, which is the same as
let's see if I've got that right, minus 1, 1, you see, and then there's 0, 0, which is very symmetric. No other components for that. So you can use the Young tableau theory to get Clebsch-Gordan coefficients pretty quickly, instead of using the raising and lowering operator stuff like go. Now, a mixed configuration has all possible spins and all possible orbits of S, P, and D. And I'm talking about uppercase S, P, and D. That's what these would be labeled. The lowercase p's, you see, are what's going into this thing. And if I have different radial quantum numbers, you're going to get all of those states in some form or other. But if it's carbon 2p squared, the Pauli principle is going to exclude, it's going to exclude this this symmetric guy here, this singlet, you see, from having a triplet of spin. The triplet of spin is symmetric. This is already symmetric. I need only an anti-symmetric spin, and the only anti-symmetric spin is the singlet, and that's what that notation refers to. So the two symmetric things, S, big S, and big D, they get to have a singlet, whereas the P, which is this one, angular momentum 1, has to stick with the triplet. It's anti-symmetric in orbit, so therefore the spin part has to be symmetric, and symmetric spin gives you a triplet, as we just showed. So they're the forbidden ones in Pauli-Fermi selection rules. For just atomic spectra, this is part of carbon's lower states. Now we can use the Young tableau to go analyze that in all kinds of beautiful ways. We can also write a formula using some of this stuff that works for all J's. So, you know, there it is. This is a formula very similar to the formula for the D's in some ways. And there are relationships which were talked about in that paper that came out in the International Journal of Molecular Science. You can visualize these things. Angular momentum J1, J2 making J3, summing, you see. It'll be a cone, and this is the old pictures that people used to draw. This is what it really looks like. And underneath there, at the edges of the cone, will be dots that form an inflection point. This is 9 cross 9 giving 18, giving 17, giving 16. You see, this one has a nice Gaussian. This is a little oscillator function in there. This is really weird. But it's true. It's what it does is you pick different values of the Clebsch-Gordan, and now you don't have an angle you can turn continuously. The angle is now discrete as well. So that's one way to look at it. The other way is uncoupled, coupled cones sitting on top of each other in a coupled way or uncoupled way. Okay, now here's where the Young tableaus come in. Let's suppose I have 3, and that's what Clebsch-Gordan is so terrible at. It just does pairs. It's kind of like what our political system is going through right now. It's just saying, hey, you got to have just man and wife, right? Or man and woman, right? And then we're going to have the Supreme Court was just doing that the other day, right? It's endless. But anyway, what have you got 3? What are you going to do with 3? You see, so they're all left out in the cold here. Okay, right? That's where Young tableau takes over because it's a democracy. You see, it puts them all together. Hey, come. We've got room for everybody equally, you see. And so how do you make this have that, you see? Now you can see what's going to happen. 1/2 cross 1/2 makes 0 plus 1. Then I'm going to cross that with a half. Okay, well the 0 is going to hit the 1/2 and just give me a half. That's easy. But 1 cross a half is going to give me 2 things. It's going to give me a 1/2 and a 3/2. You see. So it's the parentage. You have to tell who your parents are, right? And then say, oh, what if I did the parents some other way? Well, there are transformations for going between all of those choices, and they're called Rocca coefficients, recoupling coefficients. I'm not going to go that way. I want to try to do it with the tableaus. So here's the way I like to look at it. As I go up the spin ladder here, with here's n equal 2. Okay, now I'm going for n equal 3. You see, and the idea is each time I'm going to put a spin up and a down onto what I've got here. You see, so I start doing that, and for n equals 3, I get spin 3/2 and spin a half. Okay, spin a half
and spin 3/2, there's a completely symmetric combination, there's the parasymmetric combination. That's why the Young tableau are so powerful. Because most of these things are going to be parasymmetric. Only the ones on the very top here are totally symmetric, you see. So you can actually work out coefficients like this using that theory, at least part of the way. Now, the permutation multiplicity for n, okay, as I go from S2 to S3, remember I had a multiplicities of 1 and 2. Then when I went to S4, okay, we had 2, 3, and 1. Remember that was our irreducible representations. Okay, 5 has 1, 4, and 5. 6 has, this is what we used actually for SF6. Okay, and so forth, you see. This is a rather interesting set of numbers, kind of like a Pascal triangle, except it's not. Okay, but the idea is that you're going to use this multiplicity with the unitary multiplicity. That's the game that's being played. Permutation multiplicity can get summed over, and this thing is going to be left. So this is what it's showing you. And the idea is that if you add up the product of those numbers, you always come up with the total number of states: 2 to the 5th, 2 to the 6th, 2 to the 7th. You see, as I keep adding another particle to the thing. You can see it very clearly here. A triplet plus 1 gives me a 4. You see, 2 doublets, that's what the dimension of this thing is, plus 1 quartet, okay, gives me 8. That's 2 to the 3. Then when I come here, remember that was a 2-dimensional representation times a singlet. Okay, so there's a 2 there. Then there's 3 times 3 here. This is the spin multiplicity. That's the 3 that goes with that particular tableau permutation thing. Now this tableau is just symmetric, so it only has 1, but the spin part of it is angular momentum 2, so that's a quintet. So I get 5 times 1 plus 3 times 3 plus 2, that adds up to 16, and so forth. So as we work our way through this, we have a complete control of the spin part of this for any number of particles. And that's really, I think, quite beautiful, and that's where the tableau calculations are needed to, work out things like that. So I'm going to quit after just showing you a parasymmetric U3 diagram where the quantum numbers N1, N2, and N3 are being taken seriously. They would be quark numbers in high energy physics, but in atomic physics we're interested in those states as parts of the periodic chart you're in. If you've got some orbital with 3 particles, then you want to look at this thing and look at the quadrupole versus the dipole. That's what the dimensions really mean here. And that's what's going on here. Now, this is lab and state, body or particle-based operators, lab or state-based operators. Label the operators, label the particles, okay? There's the duality, and that's what we need in order to work out, for example, the eightfold way. There's the eightfold way, the 8-dimensional representation of U3, which this is a p orbital. And this is just a part of the stuff that's in that chapter 25 or 6, I forget which, of the QTCA textbook that we see. Now, I'm going to end on this. When you put Bras and Ketz together with this thing, you get our old friends, the Pauli matrices. Well, there's T11, there's T10. That is the Pauli matrix with a minus sign and a square root of 2. That's annoying because we wouldn't have put that on there. But when you do it with Pepys-Gordon coefficients, you have exactly what's needed to make the right combinations of these two that give the other, besides the sigma z. Okay, so this is another way to look at it: Tx, Ty, and Tz instead of T angular momentum. These are the standing wave bases, which do give us directly the Paulis with the square root of 2. So that's just the difference between spherical and Cartesian. Our old friends finally are recovered from this. But we now have a way to generalize this, you see. as we know, those three operators make a vector set. We've seen this. There's a rotation or reflection matrix, actually, that's showing up there. And here's what happens when you do U3. Now you're going to put the angular momentum 1 bra kits together. And you're going to get 1, 2, 3, 4, 5 components of a quadrupole, as well as 3 components of the dipole and a monopole, you see. So that's the thing that you'll find in this paper and in the textbook, Principles of Symmetry, Dynamics, and Spectroscopy. This is the way we put the U3 stuff. This is the way we put the U5 stuff for the D orbitals. This is P, D, F, and there's a G as well somewhere here. And then there's the half integral ones too. That's the Pauli spinners right there. But these are the Dirac spinners right there. And God knows what the 5 halves are, but they're all useful if you're doing JJ coupling. Those things are very helpful. So basically you have all of the irreducible tensor operators just laid out in a nice way that you can pick them out immediately and do things with them. So that's what's going on here. We're actually evaluating a Hamiltonian for our favorite x to the 4th, y to the 4th, z to the 4th. That's the Hecht Hamiltonian if you make them angular momentum. And all of that's discussed in this paper, International Journal of Molecular Science, at the beginning, which is sort of off-putting, because that's what you see when you come in to that paper, and it's not very friendly. All of the real good stuff is sort of from the midpoint on. I encourage you to look at both of them, though, because there are a lot of unsolved problems that we need to go back and look at. Well, that was a heck of a smorgasbord, and I'm glad that you could come and take this course, this weird course where we're just videotaping with, well, we don't know how many students are outside of the room, but I thank Mohammed and TC for putting up with a fire hose full of group theory, and I hope that you can make use of at least a few drops.
Thank you.